Convergence and stability are very important in the explicit method. So in order to achieve a converged solution, theoretically, the delta x and delta t must be approximate to 0. With that, when we use the center type and forward type of the numerical finite difference method to approximate the true derivatives such as the d squared t over dx squared and d squared t over dt, then our numerical differentiation will be approximately close to the actual derivative here. Then you should be able to obtain the temperature solution from the numerical formulation. And the numerical solution of the temperature at particular point xi and particular moment tl here should be converged and close to the actual temperature txt. In the example 1, lambda is equal to 0.020875, where we choose the delta x to be 2 and your delta t to be 0.1. By the Kanahan research in 1969, when you choose the lambda less than equal to 0.5, the solution that you obtain will be converged and stable. So stable solution means that the errors in any stage of the computation will not be amplified, but it will be reduced as the computation progresses. When you choose lambda to be smaller than 0.25, then you will obtain non-oscillating solution. And if you further choose the lambda less than 0.167, you can further minimize the truncation error. So as a rule of thumb, your lambda should not be more than 0.5. So if you choose more than 0.5, you will obtain diverged solution. Therefore, your delta t and delta x should be carefully selected to obtain the lambda less than 0.5. If not, if you choose the lambda greater than 0.5, you will obtain unstable solution as well as diverged solution. This is an example of divergent solution where you can see you predict the temperature exceed the boundary condition. So your heat source hit the temperature at the end here to be 100 degrees Celsius. So it is not logic to obtain the temperature higher than the heat source here. This happens when you choose the lambda greater than 0.5. And we should avoid it. This is an example for the unstable solution. You can see the temperature result is not stable. For example, for this point, the temperature increased suddenly and decreased afterward. The oscillation of the solution is not only happen at one point, but also happen at many points there. So this is due to the improper selection of delta x and delta t that cause high lambda, which is greater than 0.5. And also when you compare the actual solution at t equal to 12 here, you will notice that the lowest temperature occurs at x equal to 6. However, if you choose lambda greater than 0.5 in this case, at the x equal to 6 here, you obtain the temperature higher than the one at x equal to 4 and x equal to 8, which is not true. So this is because you have unstable solution where the error grows in the calculation due to the high truncation error. In simple, when you use the explicit method to solve the parabolic PDE, you should choose the lambda less than equal to 0.5 in order to obtain converged and stable solution. If you want to have the highest accuracy, then you can further reduce the lambda to be less than equal to 0.167. By doing that, you can minimize the truncation error. In the example 2, we repeat the example 1 but using different lambda. So in this case, we choose the lambda equal to 0.735, which is greater than 0.5. So in this case, you should expect diverse solution. And we want to check whether this condition is true or not. This is the formula for the explicit method, where you can see the lambda now is changed to 0.735. The initial condition, the boundary condition here, the delta x here, as well as the k coefficient are remain the same. The only difference is the delta t, where we have the delta t equal to 0.1 second in the example 1. In this new example, example 2, we have the delta t to be 3.52 seconds. And you should notice that this delta t is larger compared to this one, where the truncation error will be increased as well. So it will cause the numerical solution, especially the accuracy, to be reduced. From the boundary condition, you obtain the temperature 100 at this point and 50 at this point. From the initial condition, you obtain the temperature to be 0 here. Therefore, we can write the temperature information here, where you can see the subscript 0, 1, 2 until 5, indicating this 6 point at the x dimension. At the top, you have L equal to 0 here, which indicate the time at 0. In this example, we have the delta t equal to 3.52. Therefore, we obtain the next time t1 to be 3.52. And you obtain the temperature at the corner to be the same like the previous one due to the boundary condition. And we are going to predict and determine the temperature in between these points. Then we can write the temperature information here, where you can see the time index is changed to 1 from 0. To find the temperature at x1 here, at T1 equal to 3.52 seconds, we are going to find T11. By substitute the I equal to 1 and L equal to 0 inside this formula, you should be able to obtain the first equation. And then this information can be obtained from here. After you substitute inside this equation, you should obtain the answer equal to 73.5. By using the same method, you obtain the T21 to be 0, T31 to be 0, T41 to be 36.75. So you should be able to obtain this answer for T1 equal to 3.52. And you repeat to find your T2, which is equal to T1 plus the delta T. Again, at this point, due to the boundary condition, the temperature will be always 100. At this point, the temperature will be always 50. And we are going to find the temperature at these 4 points. By using the same formula, you can find the temperature at T12, where the previous index for time is 1, now you change to 2. So, to find the T12, just substitute your I equal to 1 and your L equal to 1. Then after you substitute inside this formula, you should be able to obtain this equation. And you substitute the information here to obtain the T12 result. And this is the result. Repeat the same procedure for this temperature, and these are the corresponding results. And you should be able to obtain this temperature solution at T2 equal to 7.04 seconds. You can use the same procedure to find the next time T3 equal to 10.56 seconds, and this is the temperature result. And continue the calculation for the temperature at T4, T5, and so on until you get the temperature solution to be stable and steady state. Let's check the result and make analysis to understand whether this answer is acceptable or not. We would like to know when we change the lambda greater than 0.5 in this case, does the solution become better or bad? We see unstable solution where you can see at many points the solutions are oscillating. For example, at this point, the temperature suddenly increased by 70 degrees at T1 and suddenly decreased by 40 degrees Celsius at T2 and again suddenly increased by 60 degrees Celsius at T3. The fluctuation of the temperature is too large and therefore we can say it is an unstable solution. If you continue the calculation for the example 2, this is the result for t equal to 6 seconds, 12 seconds, 18, 24 and 30 seconds. And you can see that the temperature at many points are oscillating. For example, at this point, initially it dropped and then suddenly it increased again and drop again and increase again. Not only oscillating pattern which indicate the instability, the temperature that you determine should not exceed the boundary condition here, which is equal to 100 degrees Celsius. It's not logic for you to obtain the solution at this point to be greater than 100, and also it's not logic to obtain the temperature to be close to 0 degrees Celsius. Well, the temperature next to this point is heated to such a high temperature, so it's not logic. So this indicates divergence solution, where the solution that you determine is far away from the true solution. So from these two examples, it teaches us a good lesson. When you use the explicit method, to solve the parabolic PDE. The lambda selection is very important. If you choose the lambda more than 0.5, then you will obtain divergence and unstable solution, which is not good. So we should avoid this. We should choose the lambda less or equal to 0.5, such as the example 1, and by doing this you can obtain converged and stable solution. If you want to improve the accuracy further, you should consider to reduce further the lambda